Bismillah ar-Rahman ar-Rahim. Linear programming, computer solution, and sensitivity analysis. We have already learned about graphical technique to solve linear programming problems. The graphical technique, as we learned earlier, has limitation that we cannot solve for more than two decision variables with graphical technique. Therefore, we will learn how to solve it using computer, and for that matter we will be learning related to Excel, and there is another program which is called QM for Windows, how to use that to solve bigger problems. Also, we will learn about sensitivity analysis, and sensitivity analysis is very important thing to know about linear programming, because linear programming is a deterministic technique. The parameters are fixed in linear programming, such as the profits or the costs or the technological coefficients or the right hand side of the constraints. These all parameters are sort of fixed, but the real world is more probabilistic. It's changing always. So we would like to know that how much, for example, the profit changes and still our corner point remains optimal. So, and similarly, what if we have more resources, how our solution look like, and we will learn a very interesting concept about called shadow price, which is the worth of the resource, and we will see that how much the worth of resource varies, how much the right hand side of the constraint varies such that the shadow price remains constant. So these are the things which we are going to learn in this chapter. Moreover, we will see how sensitivity analysis can be done with graphical technique. So in this chapter, we will learn about computer solution and sensitivity analysis. The computer solutions normally are the programs are which are done is using simplex method, but we will not learn the actual method which is used in solving linear programming, but we will learn how to use Excel spreadsheet and QM for Windows. Now this is the Excel spreadsheet where we can solve the problem. We just have I can show you the old problem, which was how many number of bowls to make and how many number of mugs to make. We had two products and we had two constraints also. One was labor constraint and another was clay constraint. And these were the technological coefficients in these constraints, which means that 1 hour is needed to make one bowl and 2 hours of labor is needed to make one mug. And similarly, 4 pounds of clay is needed to make one bowl, and 3 pounds of clay is needed to make one mug. And the total available to us, the resources are 40 and 120. We just fill this up like that. Table, we make a table in spreadsheet, and then we make this bowls and mugs and profit. Here the solution will come. which we will find the number of bowls and number of mugs and what is the total profit. Now, the number of bowls and number of mugs is our decision variables, right? And here the profit is then Z is equal to 40 x1 plus 50 x2. Now x1 over here is the number of bowls and x2 is number of mugs. So we need to give a formula over here, which is Z. That is objective function. So objective function is basically that 40, which is cell number C4, 40 multiplied by B10. B10 is number of bowls. So this is 40x1 plus 50x2. 50 is here is D4. D4 is 50 and B11 is number of mugs. So for 50x2. That is the total profit here. So we just fill in this formula here. Similarly, in the usage here, we fill the formula, which is that the labor hours 1 multiplied by x1 number of bowls plus 2x2, okay, is over here in this formula as shown over here. And for x1 is number of bowls and 3 is number 4x1 plus 3x2, where x2 is number of mugs, is to be filled over here. All right, and the available are over here. Okay, this leftover is slack or surplus. So the slack is whatever is unused resource is called slack. So it's just 40 minus 0. 40 is the number of hours available and usage is at the moment 0. So 40 minus 0 is 40 here. And similarly 120 minus 0 is 120 here. After that, after filling up this and making these, putting these formulas, we have to go to solver. Solver comes when we hit the data tab, and then we have over here in the analysis we will see solver. But if this is not available, then we can go into file, and there you have options. Under the options you go and go to the Excel add-in, and you can add solver from the Excel add-in. I will show you when I will go to using Excel. Okay, so here it shows that how the parameters are to be filled up, these screens in this solver screen. Okay, so here, for example, set objective, it is B12, for example. If we go back and we see that in B12 here, B12 the profit is there. So we just give the reference there, that where the objective function is, whether it is maximization or minimization. And here by changing variable cells, the variable cells were, if I go through the previous, the variable cells were number of bowls and number of mugs. And then we had, so we just fill this up, this in variables. And then there are constraints here. There are two constraints. Okay, these constraints are, if we go back, the constraints were these were the constraints, that this usage should be less or equal to 40 of labor hours, and clay is usage over here is less or equal to 120. We have to give this reference to the cells as shown over here. These are the cells, and we go and fill this up, and by adding this constraints. By adding the constraints from here, we can add these constraints. And then we have this, select this, that non-negativity constraint, which is make unconstrained variables to non-negative. And if we click on this one here, we can change to simplex LP. simplex LP is used to solve the problem. Okay, when we add the constraint, we get a new window here, and adding a model constraint here, we give the reference cell reference, which is the usage, and this is the constraint right hand side. We give this and we say add another constraint and then say okay, and we get that. These are of course slacks, and that is the solution. When we go and say solve, we get the solution. The solution is that number of bowls is equal to 24 and number of mugs is equal to 8 and the profit is equal to 1360. The leftover is telling us that there is slacks are 0. Slacks 0 mean that all the resources, both the resources have been fully used up, which we can see from here that available resources and the usage is the same. So the slack is 0. This is the solution screen. We already have in the previous screen, but we can get also the solution screen separately as well. Okay. Sometimes the constraints are not in a standard format, so we have to give them in a standard format. For example, here x3 is greater or equal to x plus x1 plus x2. Now it must be converted to, we should get the right hand side equal to some numerical value, so we just bring this two variables x1 and x2 on the left side and make the right hand side to some numerical value. In this case it is 0. Look at this one also. This is also not in a standard format. If we have a constraint x1 over x2 plus x3 greater or equal to 2, we can just manipulate this constraint, and finally we get this in a standard format. Once this is in a standard format, then we can easily give this constraint. Another program is called QM for Windows, and QM for Windows is a very easy program. It's I recommend that you should download it from the book website and use it. You can easily see your concept, you can easily test your concept. Very easy, very user friendly. You can see here there's just a slider here. When you open that QM for Windows, what you get is the module for linear programming, and from linear programming module, when you click on that, this window will appear, and you can easily select by sliding this button, you can make number of constraints more, and similarly by sliding this button you can make number of variables more. If you like, you can change. The objective function could be maximized or minimized, and when you say okay, you get a nice table here, and you just fill up the table. This table is filled up. We maximize, you will put 40, 50 and 1, 2 and 40 here and so on. And you can also change this if you have to change to greater or equal to or equality, etc. And then just say solve, and it will solve. And this is the solution of that. We get 24 number of bowls and 8 number of mugs, and 1360 is the optimal value of our objective function. And the dual, we get also the dual. Dual is the shadow price. I talked about that. We will learn about the shadow price. Shadow price is the worth of the resource. One unit of this resource is the shadow price. This is sometimes called dual value or dual price, or sometimes called shadow price. All these different names are there. It means the worth of the 1 unit of that resource. The marginal value is the dollar amount one would be willing to pay for one additional resource unit. Now, for example, it is saying that $16 is the worth of this resource, labor. So for example, if a laborer comes to us and he says that I am willing to work for $20 per hour, should we hire him? Well, the answer is that the worth of this resource is only $16. So if he is coming and he's asking for $20 per hour, then we will say that we don't need your services. On the other hand, if laborer comes and he says that I'm willing to work at $10 per hour, then of course we can hire him because he will be bringing $16 profit, and we can pay him $10 per hour. And similarly, this is the worth of the second resource, $6 per pound. So if you have more clay, it will bring $6 per pound. Okay. Another good thing about QM for Windows is that it makes the graph if there are two decision variables, so you get also a nice graph. And you also get the corner points values, profit at those corner points. So we have 4 corner points here. One is 0, 0. Of course, you will have 0 profit. And then the other one is 0, 20. 0, 20 is this corner point. And at this corner point, your Z value or profit is 1,000. And then the next is 30, 0. And you have the profit is $1,200. And this is the optimal one, which is 24, and 24 number of bowls. X1 is equal to 24 and X2 is 8, and the profit, maximum profit, is $1,360. Sensitivity analysis. Now, sensitivity analysis is when I started the lecture, I said that sensitivity analysis is very important from management point of view. We would like to know what if the objective function coefficient changes, profit changes, and would that change our optimal point or not? Similarly, what if we have more resource, and then what would be the effect on the profit, etc., or what would be the worth of the resource if we change the right hand side to a larger value or smaller value, etc. So this change in parameter values of the objective function, we can get the sensitivity output also from both from Excel as well as from QM for Windows. So we will see the changes in the objective function coefficients graphically, and how to find out the limits of these objective function coefficients. This is the same problem. We have z is equal to 40x1 plus 50x2, and there are two constraints here, x1 plus 2x2 less or equal to 40, and 4x1 plus 3x2 less or equal to 120. The solution is there, and you can see that this is the optimal here, which is z is equal to 1360, x1 is equal to 24, x2 is equal to 8, and z is equal to 1360. The dash line is ISO profit line. Now, when we change the coefficients of the objective function, this dash line will move, and the slope of that will change. So we have to see how far we can change without changing this optimal point. All right, so let's see first the effect of changing the coefficient value. Now here from instead of 40x1 we have changed to 100x1 as shown in red color here. The point has shifted from 24 8 to a new corner point which is 30 0, and the new, of course, new value is there for the objective function, but the point is that the corner point, optimal point, has been changed. Let's see. Now we have put back the 40x1 again there, but we have from 50 we have changed to 100x2, and now the slope has changed again, and now the point has shifted from point C to point A. Okay, again we can see that now the corner point is different. All right. Now the sensitivity range for an objective function coefficient is the range of value over which the current optimal solution point will remain optimal. So we have to see that what is the range over which the coefficient, profit coefficients changes, or the objective function coefficients changes, which is the profit for each variable changes, and such that the corner point remains the same. All right, so here is the objective function coefficient, and if we see the slope of the objective function, it is minus 4 over 5. You can see from here that this is minus 4 over 5. Now if the slope of the objective function changes to minus 4 over 3, the line is parallel to the constraint line. This is in the next slide. You can see over here, if this slope minus 4, 5, which is the actual slope, if we change it to minus 4 by 3, it will be parallel to one of the constraint which has the same slope, and the point from B, it shifted to point C. Okay. Similarly, if this slope, original slope of minus 4 over 5 is changed to slope minus half, then again the point will shift and the new point optimal will become 0, 20. Now how to establish this range? To establish this range, what we can do is I can write down the constraints again. Over here we have these values here. Z is equal to 40x1 plus 50x2, and we have two constraints here. Which one? The x1 plus 2x2 less or equal to 40, and 4x1 plus 3x2 less or equal to 120. Now we want to change this, we want to see how much this $40 profit, how much it changes that the range. We can find out that the optimal point, the corner point, which is B, remains optimal. One way is just to simply look at it, and we can tell that if this 40 becomes 25, then the slope 1 and 2 over here, and this will be 25 and 50, the same slope, it will change. On the other hand, this 4 and 3 is there, then this becomes 66.7, and 50, which has the same ratio as 4 and 3, it will be there. But we can do it by following few steps so that we don't make mistake. So what we do is we change from 40 to value, call it C1 here, and let's say we find out what is x1. X1 is equal to Z over C1 minus 50 x2 over C1. And let's do the same for these two constraints. X1 for the first constraint, x1 is equal to 40 over 1 minus we have 2x2 over c1. And for the second constraint, we have x1 is equal to 120 over 4 minus 3x2 over 4. All right. So now, if we make this same slope, all right, of the objective function has the same slope as one of the constraint, we can establish the range. So let's do it. We can make this okay, I can do it over here. We can say that minus 50 over c1 is equal to minus 2 over c1. Minus 2 over, not c1, sorry, over, it should be 1. Okay. It should be minus 2 over 1. All right. So this should be not c1, should be 1. Then we can see that c1 becomes equal to, c1 is equal to 25. So this is the lower limit. Similarly, if we equate minus 50 over c1 equals to minus 3 over 4, okay, then we get c1 equal to 200 divided by 3, which is 66.7. So we can write down that c1 is less or equal to 66.7 or 67, and on the upper side, lower side, we have 25. Okay, so this is, we can establish the range for c1. We can do the same process for the second coefficient, which is 50. We can establish the range for 50 also by doing the same procedure. Let's see the minimization problem here. We have minimize 6, z is equal to 6x1 plus 3x2 subject to, there are two constraints, 2x1 plus 4x2 greater or equal to 16 and 4x1 plus 3x2 greater or equal to 24. We have seen this problem earlier also in chapter 2. The same is repeated here, and we can find the sensitivity ranges also for the cost coefficients. Cost coefficients here, 6 and 3, we can see how much we can change such that it remains optimal. Now the graph is shown here, and we can see that the optimal was at this point A, which was x1 is equal to 0, x2 is equal to 8, and z is equal to 24. The other two corner points are B and C, and the isocost line shown in dashed over here, it is showing that the optimal is at the last corner point hit is at x1 is equal to 0 and x2 is equal to 8. Now if we want to establish the range for C1, we can see that if we increase the first coefficient C1, if we increase the value from 6, it will start moving towards this side, and we can keep increasing until we get to infinity. All right, this means that the point A will stay optimal. On the other hand, if we start decreasing the coefficient of x1, then the isocos line will start moving toward this side, and the point A will shift to point B. And in that case, the when it goes to coefficient goes to $4 cost, then the point A will shift to point B, and that established the range of the first range over here, C1. Similarly, we can see for C2 as well that the same isocost line, when we change from 3, we start increasing. Then after increasing to 4.5, the point it will start moving. If we start increasing the second coefficient 3, C2, if we start increasing the value, it will at 4.5 it will shift from A to B. And on the other hand, if start decreasing, we can decrease the cost to 0. It will start moving on this side, and the corner point A will stay the same, so we can move it till 0. Now, how do we do it? The same process we can repeat. We have Z is equal to, we make it C1 x1 plus 3x2, and from here we get x1 is equal to, we get x1 equals to Z over C1 minus 3x2 over C1. All right, and let's do the same for these two constraints here. We have x1 is equal to 16 over 2 minus 4x2 over 2. And we can do the same for second constraint. X1 is equal to 24 over 4 minus 3x2 over 4. All right, now we just equate as we did it in the maximization problem. We equate this, and we will see establish the range. We see over here, minus 3 over C1 is equal to minus 4 over 2. Okay, and what we get is C1 is equal to 6 over 4, which is 1.5. And then we make change to minus 3 over C1 equals to Let me go back here. Something didn't do well. Yeah, here. Minus 3 over C1 is equal to, we equate this to minus 3 over 4. And then what we get is C1 is equal to what value? We get C1 is equal to 4. Now you can see that the original value is 6. The original value is 6. Okay, the original value of cost of this variable x1 is 6, and we are getting the coefficient value 1.5 and 4. Both are downward. We didn't get any on the upward side, which means that we can increase the value to infinity and we can decrease up to 4 or up to 1.5. We have to see which one is more sensitive. The more sensitive is the one which is closer to 6, which means that if we change from 6 to 4, the corner point is going to shift from A to point B. If we further decrease it, it will shift from B to C. But before that, actually, if we change it to 1.5, it will go to point C. But before that, actually, it will be shifting from A to B. So this means that the range of C1 is up. There is no upper range, so we put infinity, and the lower range is 4. And the same way we can do for the second coefficient. All right, and I leave it to you for doing it yourself. I think we can stop it here and we will continue later.